Welcome to entropy, which is a word that unfortunately looks an awful lot like the word enthalpy. I will sometimes in jest write entropy like this, just to kind of help. Remember, that's the one that looks all crazy and it's about craziness. And enthalpy, I'll often say that it's on fire because it's the one that has to do with heat. So try keeping track that entropy is craziness and it's crazy entropy. So what entropy is a concept that's kind of weird to talk about at first. So I'm going to give you some different descriptions and try to help you wrap your head around some of this. If you want more math or more descriptions, there are plenty in the playlist because it's a topic especially physicists love to talk about. So some people will oversimplify entropy and just call it disorder. And this can be a good way to talk about it, but it can also it can add in implications that aren't there. So the more positive that entropy is, the more disorder. Or you could also say chaos. So I'm going to give an example of why we sometimes people will use disorder to describe it, but then we're going to move on and kind of talk about it a little bit differently also in terms of probability. So over here, when you look at those, and remember, these are all like in motion. So if you like screenshot that in your head and then a second later you screenshot it, it's still going to kind of sort of be really close to where it was. The vibrations might be slightly different, because they're going to have been in, moved just a tiniest bit, but it's going to be fairly ordered, although it won't be perfectly the same every snapshot because of the vibrations. Then if you remember the liquids over here, these are in this layer and they are moving. And so any snapshot where you were paying attention to this one or this one in your head, if you take a snapshot and then another snapshot, well, this one might interact with that one and this one in the meantime between you taking these snapshots. So the atoms themselves are going to have more entropy, more disorder, more chaos, because they can move and be in a lot more potential places, aka it's harder to predict where they're going to be. And then finally, a gas, it's not just staying in that surface and bumping tightly off of each other, because those molecules are still pretty flat. I mean, not flat, but they're like close into each other for the liquid. But with the gas, they're bouncing off of each other. They're bouncing off the edge of the flask. They are moving faster. And so again, the predictability, the probability, the likelihood that the screenshot in your head of these at one picture in time and then at the next picture in time is going to be showing that it's less and less likely for you to get the same picture or predict the same picture. And the more unlikely it is, the more disorder chaos you're talking about, which means increasing entropy. So this would have a more positive entropy. This would still be a positive entropy, but this would be like a larger number. And this would also still be positive, but this would be larger than the solid. So that's one way to look at entropy, is like if you screenshot it and you keep trying to do predictive screenshots, it gets harder and harder the more motion and movement and everything that you've got. So because we don't like to have disorder, we will try to box up this energy and this movement into a pretty picture. And we will do this. Now, what this is this is actually probability. And what this is saying is, so we can model these systems with just 4 atoms. And to make it even easier, we can say those 4 atoms can only be in 4 corners of a box. And I'm pausing because if you think about this, there is no boxing in those pictures, right? So we're making a lot of assumptions just to try to make this more explainable, okay? So we're just taking 4 atoms and we're just saying, oh, well, we can make some predictions about them, kind of is what we're saying. So the way that you can arrange 4 atoms in one part of the flask versus another part. So imagine we're trying to move them we're waiting and then they're all moving to another part. Again, you can see this is a lot of assumptioning. These could all be on the same side, but it's not very likely that that's going to happen. They could also all be on this side. Most likely it's going to be somewhere in between. So maybe there'll be 3 that are left. And notice that the color of the one, there could be one there, or this one, or this one, or this one. all right? Or you could have pairs. Actually, here's the threes again, the other direction. So we have 3 on one side and then 1 on the other. Or you could do pairs, and you could kind of see like all these different arrangements of how they've got pairs possible. So this may, if you've had statistics or if you've looked at like throwing dice kind of a thing, like the likelihood that you're going to make a, prediction, whatever. Well, this scenario right here is the one that is going to be giving us the most entropy, because there are lots of places that you can imagine these molecules having been. So we call this states. The more state combinations, so this one has 1, 2, 3, 4, 5, 6. The more state combinations you have, the more likely it is. So I'm going to give one more description that kind of moves away from chemistry that might kind of also help wrap your idea around what is entropy. It kind of has to do with when and where something is and predicting it over time. And those predictions help us determine how much energy is being used in those processes. But it's also, you can get to understanding entropy and that number just by having kind of like a general idea of it. If you were to go on and take something called physical chemistry or higher level maths, you might start looking at something like this. So my very last picture is about a Disney movie. Now, for the life of me, and I've researched this over and over, and if you know the answer to this and want to message me, that would be awesome. But I remember that there was a Disney movie, and this involved either hair or fur, and so I'm pretty sure it was hair, though. And I want to say that maybe it was Frozen. But when they were trying to do the calculations, because this is all programming now, the hair that you see on the screen, what it's doing. And between like the first one and the second one, the ability of the programs got a lot better. And so the programs were suddenly able to basically move more hairs at a time. And obviously the math was more complicated, and it just wasn't possible. They didn't even have the programming that would do it in that movie, but they did by this next movie. And so then that shows you it's more, it looks more realistic. If you think of all the hairs on your head, and then think about predicting like which hairs are going to bounce off each other, which ones are going to be more higher, which ones will be lower, which one will have a little static electricity. That is all increased entropy in the system of your hair, basically. And so if you think of that Disney picture, this is the one that's got a whole lot more entropy, and then this one is the one that has less entropy. And I'm not saying it doesn't have entropy, but comparatively, this is the one where when they have all of the hairs doing all different things, that's the one that shows the greater enthalpy. So hopefully that gets you an idea of what enthalpy is about.